There you go. Okay, so we did this problem last time. We were trading off processor and memory. And appropriate for the motherboard that's going around, you can actually see the address bus and data bus. And this is a functional abstraction, but here's the physical view. We're going to see another physical view today that helps us get started with what these things do and processor, and we're going to look inside these boxes. We said, right, we're going to start with the so-called black box view, then we go to the clear box view, we go inside here. We're going to see a mechanical view. First mechanical view. But if you look on a printed circuit board, okay, it's printed, these are copper wire traces on an epoxy resin piece of plastic. And this is actually a little daughter card, is a memory module. These are memory chips. Okay, we'll get talking about that. So, I think we didn't do this problem, right? Did we do this one? No. So, computer system, let's put some numbers in and try some examples. So, the computer system has a single core, 32-bit processor. Everything we're doing right now is single core. I'll tell you later on single core. So, 32-bit processor, 8 gigabytes of addressable memory. There's two items. What's the minimum number of wires on its data bus? So, first question, what does it say data bus? What is it referring to? Data bus. All right, go back to here. I want to know how many wires are on that channel. It's just a fat arrow on Microsoft PowerPoint, but we know in real life those are copper. That's 32. And why? This is a 32-bit processor. The number of bits that the processor is 64-bit processor, 32-bit processor, 8-bit processor, is exactly the width of the data bus. It is the number of bits that get crunched in every instruction. This processor crunches 32 bits at one time. Therefore, it must have 32 wires on its data bus. For sure. If you take that chip and you look at it, look in the log sign up, Motorola 68000 microprocessor, the Mac 1, okay, looks like a little toaster. Back in our Internet of Things, right? Back then the big thing was computer appliance. They want everything like an appliance. You just plug it in the wall like you did a blender, actually, or a toaster. And this is that guy. They look like that. And if you're an artist, you think that's cool or cute or whatever word you like, and they all bought it, right? Graphics and things. Kind of interesting. That was that processor you'll see actually has 16-bit address, but here's 32. What's the next question? Minimum number of wires on the address bus from processor to memory. 32 could be what? This is address bus. So this is data bus. I agree with 32. Address bus is going to be the capacity of the memory. So we have 8 gigabytes of byte addressable memory. Now this is where it gets a little tricky, but it's actually not that tricky. We just have to keep track of this. In this class, all memory is byte addressable. It's not that big leap of faith. We're not candy coating things too much. All memory that you buy is always byte addressable. What does that mean? Even if it's gigabytes and you access 32 bits at a time, I can drill down to a resolution of a single byte. How many bytes is 32 bits? 4. So the processor is transferring a 32-bit word between processor and memory, but it can do so at the resolution of 8 bits. Okay, so what this is saying is that we have byte addressable memory. What that means is I can access it on a byte-by-byte basis. You're going to say, I'm still confused. So the right model here is just like mile markers on a road. Okay. Now we have GPS, so you don't track these anymore. But there's exits such and such at 232. Then you drive down the road, they're marked in tenths. So the units are tenths, right? 232.1, 232.3, or whatever, right? They're tenths of a mile. But you access the mile, the next exit, right? If you remember 5 miles is how you access that device. So in this case, we can access down to the byte level. It's byte addressable. And what's the capacity? How many bytes? 8 gigabytes. So what is 8 gigabytes as a number? Well, this is 8 This is giga. It's 2 to the 33. So I have to access 2 to the 33 distinct locations. That's the resolution. In other words, if I told you that the highway was marked in 10, okay, and there was 1,000 miles, how many mile markers are there on the highway? It's marked in tenths. It's a 1,000-mile highway. 10,000. Okay. So same thing here. Okay, this is the number of bytes in the 8 gigabyte space. So I have to access that, but I'm using binary. A binary number, how many digits? Bit is a digit, right? How many digits in that binary number to get to 8 giga? Different choices. 33. Why? Because 2 to the 33 is 8 giga. Same thing as if I told you, I have 1,000 post office boxes. How many digits do I need in the post office P.O. box? This is the post office. Here's the address. Data's inside, right? Each box, right? What box number is this? 0 up to 999. How many decimal digits? 3. Why do we get 10? Why do we get 1,000? Because 10 to the 3 is 1,000. Everybody can do that. It's a mental block, right? A mental block. But here I have 33 binary digits. What does that look like? Well, that's a lot of ones and zeros. This can be a 0 or 1, and this can be all these guys in the middle, and this is 0, 1 here, and a 0, 1, and 0, 1. How many of them? If I give you 33 of these, what's bit stand for? Binary digits. You get 33 binary digits. What's the addressable range? 2 to 3. So, if this is a 8 gig addressable range, I look at this chip, look at this motherboard, I can see, right, at least 33 wires. Why might there be 33 in a minute? Why might there be more than 33 wires on the circuit board?
Support for more memory?
Yeah, because you can upgrade the memory to 16 gig. How many more wires would you need to go from 8 to 16? 1. 1 more wire. Why? It is 1 more wire. Because every time you add an address bit, this is the key takeaway, make a note in your notes or make a mental note, or just make it sure it makes sense to you. Every time you add an address bit, you double the addressable range. It adds up, right? It starts, it's a multiplicative price. So, we get to 8 to 16 to 32, and that's what the powers of 2. Just know your powers of 2, because every time you add an address bit, that's why memory is sold in units of 2, because it has to be addressed. We use binary to address things. That's why nobody sells you a 13 gigabyte flash. Because they need, they can access 16, right? If they give you that address bit to access 13. So we talked about our 5 basic food groups for computer systems. Memory, control path, data path, input and output. We said control and data are part of the processor. Input and output devices are electromechanical devices. And here we see something connecting these together, which your author uses the word link. This works for me. This dotted box is the computer system boundary. You go outside of that, you're at the network level. Where we said before, we start with the transistor level. You say device. You get gates. When you build gates, you build register level components, muxes, shift registers. Then you can build component level things like memories, processors, out of register level components. And out of that, you can build systems. You go outside of that, you get to the network. We said this before, we'll say it again just because my clustering analysis shows disappointing confusion after many years of data points. So again, processor and CPU are 2 words for the same thing. The processor contains both control path and data path. We're going to start to see today what those things are, what those words mean. Another source of confusion I noticed over the years, you can just eliminate it in one sentence. So what's the difference between memory drive can't be a chip like an SSD, but there's one major difference. This memory is something that the processor has access to, which we'll see. The input-output devices have to write data into memory, and the processor can access it. So we say that it's memory, or we use the words main memory, is different than a hard drive. So people that don't have a degree in electrical computer engineering say, you know, I need to add more memory to my computer, and I'm picturing they're going to go buy a memory module, but actually they buy a hard drive. Oh yeah. So you get, they don't see the difference. It is storage. This is type of storage. This is type of storage. We use the word secondary storage here. These can be electromechanical devices. They tend to be slow but high capacity. These tend to be faster. These tend to be volatile. Turn the power off, data goes away. These are non-volatile. They're different types of storage. The ones that are volatile and fast, we call memory. We use the word main. And link, there's different types of link. There's a link internally to connect up these components in the computer system. Different types of buses actually are links. And then we have links going outside the computer system, which are network links. An example of a link inside would be front side bus or south bridge. We'll give you some examples. So here's a motherboard. And we identify these different components. This is a physical view. Can anybody show me the processor? So here's a functional view. Where's the processor on it? There you go. Yeah, this processor socket. The color code is okay. And then how about memory? There's a lot of memory. There's no memory populating these slots. You're exactly right. So the memory slots. And if it's a gaming motherboard, you have some that are high speed and low speed. There's different colors, and you don't need to worry about that. That's the computer architecture class. But the point here is that you look on this circuit board. If it's not in a multi-layer that you're not being able to see, you can see the address bus and data bus. They really exist. It's not just on a slide. It's really there. How about some input-output channels? Okay, well, here's for your disk drive and maybe some I/O device and USB, and those are our types of I/O devices. Okay, we're not seeing the actual I/O device, but we're seeing the input-output channel. And here is one interface that allows the processor to talk to slower devices. We'll see what these words are later. But depends on your chipset. Actually, Intel now integrates these into one chipset. If you have a 2-year-old processor, you'll have North Bridge, South Bridge. We'll show you what those are later. Types of links. So the other thing to keep in mind is that we can build these components on a board, or we can integrate these on a single chip. And you'll see here this AMD chip. Here's a 4-core chip. You look inside each core, you can actually see the structure, the regularity of this design. Actually, what they do is they design different elements. These are memory elements that are on chip called cache. When memory is on chip, it's called cache. And we have different levels of cache. We're going to talk about what these components are, how they work together. But we can see also different elements of the processor. There's something called execution, which is control path. Control path is taking in bits and turning on certain operations, certain instructions, certain steps that have to be performed. And there's also data that gets crunched in the data path. Here's one part of the data path. This is a floating point unit. So there's actually gates here, Boolean gates that are the same full adder you learned in 3342. We're going to expand that to not just one bit, but multiple bits, and then we're going to make work with fractions. It's floating. So we're going to see what these components are and how they function. And you can see each one of these is kind of the same design. That's how we scale it up. We design one little part of this device, okay, and we get it to work, and we make copies of it to go from 1 bit to 64 bits. And then we make multiple cores. So to understand how these work, we're going to continue to use a spiral model. We start at the high level and get more and more specific. That's called abstraction. And key abstraction is the instruction set architecture. So instruction set architecture, as mentioned before, is the interface between hardware and software. And to understand how these work and be proficient at it, you want to be able to consider these types of design parameters. And things like the technology. Is this a 22 nanometer or is it 0.6 micron? What kind of high-level language do you support? What are your constraints? What does your customer care about? Does it need to be backward compatible? And these things become very practical. Companies like Intel totally emphasize backward compatibility, but that makes their chip complicated because they can actually still run the same program that you ran in a 1980 PC, 1981 PC-1, 8-bit processor. And so you end up with these very complex instruction sets. Some are 8 bits, some are 32, some are 64, and they want to run all these just so that their customers that have invested in the software, it's nice, it protects them, but also it makes the hardware very complicated. So there's some trade-offs with all of these. So you can think of a computer architect just like someone that designs a building, the architect of the building, to really consider all these aspects. Remember, architecture is something that the programmer can see. So a building architect, any attributes, the number of floors, the number of doors in the room, the number of windows, is something that the user, that structure can see. So we're going to cover these from a few different perspectives. We actually have a couple modules on each one of these. How to design these considerations, how to measure, which is independent of the customer. It's just a number, it's just a fact. So many gigahertz, so many bits of it. And then evaluate the trade-offs, time versus space, for whatever the customer wants, and what's a good choice. Here is our hierarchy of abstractions. This module is called Computer Abstractions. And we think of it getting more abstract as we go up this hierarchy. So if something's abstract, it means it's nebulous, it's general, it's generic. If something is not abstract, it's very specific, there's not many choices. Okay, so 2-input AND gate, 2 binary inputs and 1 output, it's very specific. Okay. But a program that does something, a word processor, it's pretty abstract. So we have to bridge all these levels. You see hardware, firmware, software. Firmware is actually software that's encoded in hardware. We call it firmware. But you can see some examples here. And the key thing to know from this slide is increasing level of abstraction as we go on. Things get more abstract. So what does this mean to you? We're going to see some examples in lab. If you didn't have lab already, you'll have lab after this. And you're going to be working with an assembler called Mars. Make some of these things real. But you start with application program. Anybody give an example? Raise your hand. Application program that you maybe use every day. Word. Microsoft Word is the first thing that came to my mind. Application program is something that the non-technical user use. Maybe it's a database program, maybe it's a browser. Those are all written in high-level language. Maybe Java, maybe C, depends what you want to do. Each language is geared towards a certain type of application set, certain behavior. These are all machine independent. When I compile it, I end up with assembly language, which is what we're seeing. So we start with a high-level language. I compile it, I end up with assembly. Start with assembly, you get to machine language. We'll explain what the difference are. Assembly language is something that's human readable, but it's not high level. It's very, very specific. Moving some bits around, moving from one register to another, which will explain what that means. Making a decision, if this bit is set, do something. It's very specific, not only to what you want to perform, but also to the machine. In other words, Intel has a certain set of assembly language instructions, and MIPS has another, ARM has another, NVIDIA has another. They may be customized to what the chip needs to do. If it's a GPU, it's going to be able to operate on very wide data paths, on 28 bits, and crunch a lot of pixels at one time. But if it's a processor that has to be an embedded controller and low energy, the instruction set may be very limited and not too many bits at one time. So the assembler takes the assembly language, which are these fundamental statements that are human readable, and translates them into bit patterns. These bit patterns are what the hardware actually executes. The key takeaway. When we run an application program, somebody wrote that in a high-level language, which no computer can run. So it actually gets translated to assembly, whether you see it or not. If you run Visual Studio, you start with high-level language like C, you create the executable. It actually did create this, but it creates it in a temporary folder. It doesn't show you unless you ask to save it. And then generates the machine language, which can actually run on the hardware. So let's see an example. Examples worth 1,000 words, right? So here's an example. Anybody able to abstract this what this program does? It swaps two variables. So one way to do it is to use a temporary variable, move to temporary. There's three statements in this high-level language. You put that into your compiler, you end up with a textual representation of the CPU instructions. We call that assembly. This is what it looks like in MIPS. The next module, which is very soon, you'll know what these things are. MIPS, the good news, MIPS only has about 40 instructions, 50. And we're only going to learn about 20. Okay. If you start with Intel, Intel has 400. And some are 8 bits, and then they put all these suffixes. It's like learning English. You know, there's different tenses and different. We just keep it simple just to start out. Otherwise, it gets too confusing all at once. So these are MIPS instructions. So what's the difference between a statement and an instruction? Well, you can see here there's a one-to-many mapping. We have 3 instructions, but this one instruction might map to these two. This one statement might map to these 2 instructions. It depends on the statement and what you're doing. And the machine may not be able to execute it in one step. So we have to decompose it to multiple steps. So you're going to say, okay, I see this. Can I run this? No, there's no computer on the planet that can, even MIPS processor cannot take SLL space, $, and equals, these are registers, and do anything with it. This is just for the humans. So the assembler takes this and translates this to a sequence of bits. It turns out that each one of those bits has a meaning. That's another point for today's module, is that this is the field that actually tells you, you see, what instruction it is. This may be artificial here, but we're going to see real ones very soon. Okay, I'm going to use Mars. And this is the next field, and this may be some constants and things. All the bits have meanings. These are actually hardware instructions, which are simple bits. So what runs on your hardware is literally a stream of bits. These bits are directing the control unit. They're actually inputs to the control unit to turn on and off different circuits. How do you think we turn on and off different circuits? Well, if this is a 1, it's connected to the right type of gate, I can turn on or off the circuit I want to be activated when this instruction is executed. Is it that simple? That's it. That's all a computer does. If you have this appreciation for how elegant visual systems are, it makes them, to me, seem cool. And it's really interesting to me that we can take something that's so complex, like a word processor, and break it down into these tiny, tiny steps and design hardware that's so simple. We just execute this over and over again, is what we're going to learn today. Here's another view of that process, going from something that's abstract to something that's very specific, it's actually machine specific. And this leads us to the concept of semantic gap. So we asked last time in this class, and you guys knew what's the difference between syntax and semantics. Semantics is the meaning, it's the intent. So the programmer has a certain intent that's specified with the syntax. You know, you say the swap, and then you say the variable you want to swap. That's the syntax, but there's semantics, so that means interchange. And what actually executes is over here. These are hex digits. These are really bits. But humans don't do good with a lot of bits, so for human readability, we use hex, right? So here's a hex number. A5. Okay, A5. This is 2 hex digits. How may we represent that in binary? How many hex digits? How many binary digits per hex digit?
4.
You got it. 4. In case you forget, how would you be able to figure it out? I'll give you a couple ways. So someone give me some ideas.
2 to 4 is
2 to 4 is 16. I like that. If you're a SAT type person in Latin roots and all those things, hex stands for hexadecimal. What is that? 6 plus 10. There you go. Hexadecimal, 16. So A is 1 more than 9, which is 10. That's an 8. No 4s. A 2. No 1s. It's 10. These 2. You're going to say, that's cool. Another way to remember this is a little memory aid or something. See the 10s? It's 10. A is 10. It's 1, 0, base 10. And what about 5? How many hex digits? 1 hex digit goes to 4 binary digits. 5 is no 8s, 4, no 2s, and no 1. So you're going to say, I thought you told me. I thought you told me that when we execute machine instructions, they're binary. But this is not binary. Yeah, this is binary, just written in hex. Because it's easy to go back and forth without a calculator between hex and binary. Just take 1 digit at a time and write the 4 bits. And we're going to do that a lot. So that's another reason to know your powers of 2. So, it's totally human readability. If we had 32 bits here, it's like you cannot even see it, right? It's too much. But here we can communicate to one another as humans. When do you want to communicate as humans? Well, the department meeting, project meeting, and this value means something. It's the bit pattern for a certain instruction, or you hook up you're doing the next lab, is the embedded systems. You're going to hook up a logic analyzer, and you're going to watch the bits flow across the data bus. They really exist? Yeah, and you put little probes, 32 of them for a 32-bit processor, on each pin of the data bus on the circuit board, and it's going to capture it with the clock, and it just has a shift register and loads it. You say, that's it? Yeah, that's it. But once you've captured all those bits, it doesn't want to give you 32 of them on the screen, so it gives you a hex number, which goes on the data bus. You can actually see the data flying by. That's another reason to picture bits in motion. If you can picture bits in motion, you can debug hardware, because you understand what it's doing. So we have this word called semantic gap, is the distance between what the programmer wants to realize and what the hardware is capable of. There's all different types of ranges in here. Okay, you can have very, very simple hardware, we said before, right? You can have a hardware multiplier, we can have the multiply done through a software loop. Well, if it's doing a software loop, the semantic gap is very wide. We have hardware support, and we're closing that semantic gap. So you're going to ask a good question. Why don't we just make the hardware do exactly this? You can do that. People have tried a few times, but it was never commercially successful because it's too hard to design. It's too hard to debug. Technology is always changing, and it's too complicated. So what we do is we break them into these simple instructions, and we use software to bridge the gap and make the compiling. And it turns out to be a more sustainable model. Actually better performance. We can optimize these. These turn to, if the semantic gap is too narrow, people designed these machines a long time ago, even when I was a PhD student. But the problem is that it's too complicated. And then you can't take advantage of regularity, pipelining, and all things that make computers go fast. They become too difficult. So we'll talk more about it. So CPU instructions is pretty much everything I just said. We start with the high-level language statements, so we get to machine instructions, which assembly language is the human-readable form, machine code is the bit pattern. These are some space versus time trade-off. What do I mean? Well, there's multiple mappings. I might specify this functionality with this set of C statements, right? But I might have another algorithm, suppose it's sorting, right? There's all different ways to sort. Anybody take CS1 yet? So you probably learn like quick sort, bubble sort, and it's the same function, right? It's organizing a list in the numerical order, increasing or decreasing. But algorithmically, there's different ways you can pair things at a time. You can keep the list sorted and insert values, insert sort. There's merge sort. You make sublists and merge them like decks of cards, pick a card. There's a whole bunch of ways. Well, what's better? There's different parameters, but I can make that map into the statements that's specifying the actual choice of algorithm. But then once I have this, boy, there's probably 10 or 15 different choices of how I make the assembly. I can do this before this or this after that, but I have to do that before I do this. There's certain constraints. That's what the compiler's job is to help us make those space-time trade-offs. Let's try an example. You're going to say, okay, I need an example. I agree. So, you work for Microsoft. If you do, you're probably happy. You get nice stock options, and they're probably always going to be there. So, what do you do at Microsoft? You work in the hardware platform support. Sounds cool. And a cocktail party to say that, but what does it mean? Okay, you help sell compilers. Okay, so you're at a trade show, and you're showcasing Visual Studio's new release, and you're talking to this client. Okay, and the client wants to improve the performance of their program. There's something called compiler optimization. Has anybody ever used compiler optimization? Anybody ever write code for a company or maybe your own consulting business? We do go through different waves. Like 5 years ago, everybody wanted to have their own business. People still want to do that? They don't want to do it. But if you write code, you have different compiling options. There's things called optimization. And Visual Studio actually has multiple optimization levels, but these are 3 real ones that it does have. This is the default, is no optimization. It's called the baseline translation. And here is a data sheet. Okay, which is on a little placard. It's probably laminated or something. It's in your, and you pull this out. This is going to tell you how the optimization and translation trade-offs work for Visual Studio for some typical programs. So here it says that the client's machine is a 64-bit machine code and 64 bits per instruction. Optimization levels are listed. We pronounce this 00, 01, 02. This is optimization 0, optimization 1. C++ compiles to, we're making this simple, 2048 machine instructions. Is that a number we might recognize? 2048. Yes, it is 2 to the 11th. 2 to the 10 is 1024. Double 2 to the 11th, because we have 1 bit. 2048. Executes in 100 milliseconds. In human terms, how much is that? How much of a second is 100 milliseconds? 10. It's 1/10. 100 milliseconds in a second. So, client asks you, this is I have this program and it takes this long. Why should I buy your Visual Studio update that has these new optimizations in it? And you want to sell it to them because actually the client is the representative from Lockheed Martin, and they're going to sell 10,000 seats. You get commission. You're going to make a lot of money if you can sell it to this guy. So, of course, you want to tell them what's accurate, because if you don't, they're just going to be very mad. You're going to have to give all that money back. So you want to tell them the right thing. So we're going to solve this problem. What do we need to do? First, we need to figure out the size of the client's code in bytes. Well, there's 2048 machine instructions. How many bytes is it? Well, each instruction is 64 bits. How many bytes is that? 8. Okay. So each instruction is 8 bits. So we have, as somebody said, 2K. 2K instruction. 64 bits per instruction. This multiplied by 1. So instructions cancel. Bits cancel. We get units of bytes. Can I do that without a calculator? By using powers of 2. So 11 plus 6. And why did I subtract 3? Because you're dividing it by 8. It's 2 to the 14. What is 2 to the 14 as a number? It's 2 to the 4 times 2 to the 10. What's 2 to the 10 is a K. What's 2 to the 4? 16. We just said hex. 2 to the 4 right there. 16 kilobytes. So why did I compute that in my head while the client is standing there? And that's why we show you this. Because according to this table, if you start with 1K and you turn on this optimization, you cut the code size in half. Well, this client is telling you, I'm starting with 16K bytes. If you use 01, how big is this code going to turn out? 8K bytes. And how long does it take to execute? Okay, so what's this table telling us? Is if you start with a 1K program, you use 01, it's minimizing the size, it cuts it in half. And what's the cost? So you cut it in half, the size, but then what? Took longer to run. Okay. So maybe it needs you say, well, why do I want to cut the code size in half? Well, maybe it's the IoT sensor and there's not much memory space there. And it needs to fit in that. You need to get to the moon on 4K page, 4 pages of text, 4K, right? 4 pages of text, well, you need that optimization. What's the cost? It's going to run slower as it expresses a percent. How much slower does it run under a 1? 20% slower. So how do we equate this to his numbers? Well, we see here that this is a factor of 16 larger. So you're going to start with 16, cut it in half. You're going to end up with 8K is the size, right? Okay. And what about the speed? Okay, what about the speed? Well, it's going to be 20% more. So originally it took 100 milliseconds, so under 01, 120. 8K, like we said, cut it in half from 16. What about 02? The client says, no, wait, no, I need to go fast. I don't care how large the code is. So you start with 16 K bytes of code, and he turns on 02.
32.
Okay, 32. Any other answers? 16 megabytes. I think it's 16 megabytes. Because the 1K went to 1 megabyte, 16K, no, 16 megabytes. What's the ratio between this and this? Is it factor 10? Is it 20%? No. It's a what? It's a factor of a K, right? A K times a K is a meg. A K is 1024. This number is 1024 times bigger. That's more than 1,000 times bigger. So this problem is getting us used to units, getting used to translation, getting used to what a compiler is, what's an instruction, what's a byte, what's a bit. So I just copied these to the next slide because they're in no space. Just summarizing what we just said. Question. What statements can you elaborate to the client using Microsoft's compiler technology? People are getting tired. Make it true or false. Make it binary. Okay. True or false. Modifying the translation from C++ to machine code using a translation option of 01 or 02, either one of those two, can reduce the number of instructions from 2048 to 1024. True or false? How many people say true? It is true. Which 01? Which would it be? 01. Your client wants to do that. 01. Here's a sign here. 10,000. Suddenly. Okay. 10,000. Next question. True or false? Optimization choices allow the program to execute faster by making the code smaller. Normally, if we have a long program, we expect it's going to take longer to run. How does this thing work? It's false. Why? It takes more space, but that means more instructions. But I said instruction takes time to execute, so why is it going faster? So here's something we're going to see in another slide. Another module, but we get you started thinking about it. We get you intrigued because then we solve the problems. You have to make it interesting. That's how we learn, right? Because it makes us want to learn. It turns out that a lot of program time is spent in loops. You have 1 to 1 million, you go there, you go round and around and around. To execute a loop, you have the loop body as the statements inside. What else do you have to do to execute a loop? You have to increment I. You have to test if I is greater than less than the limit. Incrementing I takes time. We're going to see it as an add instruction. What about testing if I is greater than or less than the loop limit? That takes time. That's a branch instruction. What's one way to make your program faster? Tap it all out. We unroll the loop. Okay? And what we do is we make an instance in space instead of time, right? Instead of time, we make an instance in space of every iteration of the loop. Your program is 1,000 times bigger if the loop size is 1,000, right? But guess what? You don't have to test it. You don't have to increment a counter. You don't have to test it every time because you're actually making a case when I is 1, a case size 2, a case size 3. You stack them on top of one another. It becomes what we call straight line code. Straight line code is the fastest code in the world. One instruction after another. No branching, no testing, no jumping, no. We'll explain what those words mean. But I saw another cool thing. Right. Sometimes longer code runs faster. That's the space versus time trade-off. If it's a small code in the loop, the size is very small. Time complexity may be large. Because I have to test the loop counter, I have to increment the loop counter, test exceptions, I have to branch back up, which we're going to see is a slow process, and we'll explain why later. Good for question.
So you're saying loop unrolling, you would have to write the loop body as many times as it would increment?
Exactly.
And they kind of have backflow if it's large?
If the loop's 1,000,
Yeah.
1,024, you get exactly this.
Don't you have to write 1,000 times in the code?
So if you start with 1K,
You don't.
Yeah, we don't.
I would have.
you okay, oh good, I see the word you. So so this is another thing, you'll get used to this is too, and it confuses me, and I don't want to confuse you, and I probably say that we personify these things, even though they're things, right? We say he does this, or when we say you, and the compiler will unroll.
Oh.
That's what this means. You put the /O2, and you tell the compiler to unroll this thing, you don't have to touch it. You just write it once, and it's going to make a huge. What's the problem? You can't debug it, right? And you're going to say, I'm so glad I hate loops. And I see that's another clustering analysis. I notice over time students, but I think it's good to know a little bit of loops, even if you're like what you think is a pure electrical engineer and you never want to touch a computer in your life. You probably will touch a computer. You're going to write MATLAB and you're going to write a simulator and DSP and the first day work. So you're going to use loops because your code's easy to develop. You shouldn't use loops, but if you want to run fast, we can unroll the loop. And we eliminate some steps every iteration. That's enough for now. We're going to make it more detailed later. Here is an example of an assembler. If you had lab already, you know what the screen is, and we'll talk about it in more detail, but here is assembly language. These have different purposes and roles in life. Okay, these are comments, this is semantics. So a comment is a hashtag. And then here is different labels. Labels are like addresses, okay, they're virtual addresses. And we have our instructions, your assembly instructions. Well, let's explain what these are. And then here's the register file. Remember we had the example, we had to add 1 plus 2 plus 3. We added 1 plus 2. We had the number of 3, which is sum of 1 plus 2. It was inside the processor. And somebody asked a really insightful question, where is it? It's going to be in one of these registers. We're going to explain what these are in person. Registers store values. Actually, each one of these is a data value. There's actually only 32 of them, which is the difference between registers and memory. You have gigabytes. In memory, gigabytes. Registers, you only have, most machines have less than 100, maybe 32. We'll explain why. But in this case, one of these values, one of these registers, this is representing hex, which is another thing I don't want anybody to miss this ever. If someone says this and any numbers and letters and stuff, this means hex. This is from C language, okay, and 0x, they always start with 0, there's, you can send you a link, but X is for hex, I probably wouldn't have chose X, I chose H or something, some languages do actually, this means hex. So this is a hex value. How many hex digits do we have here? 8. Yeah. How many bits per register? You don't know what these are yet, these are registers, but this is a register. How many bits are stored in this register? You have 8. 64. Nope. You have 8 hexadecimal. 32, because each one's 4 times 8, 32. It turns out this is the 32 MIPS. Actually 64-bit version. We use MIPS 32. So in this class, it's a 32-bit processor. I pick up a MIPS chip. I look at the bottom, I see 32 data lines. Because it's a 32-bit processor. I look inside, every value stored is 32 bits. You say, well, suppose I only need 8 bits. Well, we just use the lower 8 bits, and the other ones we just ignore. We're going to show you that. So this is a way of looking inside the chip at the hardware-software interface. You're going to say, well, why do I want to learn anything about software? Because I'm an electrical and computer engineer. Because it's just like saying, you want to be a baseball player, but you don't want to know what things baseball players do. Okay, what's a home run? What's a hit? What's a double? You need to know. That's maybe software, and you want to do the mechanics. You just want to train, right? You just want to assembly language helps us to understand how the hardware operates. It's only about a third of the class, but once we cover these 20 different instructions, you'll know enough to be able to design the hardware for these. But if you never learn what the hardware does, it's like someone asks you to design a circuit, which you don't know what it is. So it's going to show us how the hardware operates. There's other reasons. I guarantee in your career you're going to interface with assembly language. As a matter of fact, your next course, Embedded Systems, you're going to use assembly language to interface C with a real device, a USB port, okay, or a capacitive touch display. Data's coming in as bits. You need to use assembly language instructions to extract the middle bits that are the value and throw away some control information and some handshaking stuff. It also allows us to trade off time and space efficiency very, very accurately, because remember, what we write over here may be mapped in different ways. That was this, right? Different ways to map it. When you work in assembly, you have full control of that. If you can cut out an instruction in a loop that's executed millions of times per second, which is what we do, and this is something that's on the Google data center, right? On all these servers, you're saving them a lot of energy. You get a raise. And you go home and you feel good because you made the world greener or whatever. Accessibility to system hardware. When we work with assembly, you're working with the actual machine instructions. And I already mentioned this, trading off time versus space efficiency. You can find these sources of program inefficiency because you can see the bits flow. Okay? If you're a computer scientist, you're thinking at a different level of abstraction. You're enamored, right, with the bubble sort and the quick sort and the shell sort and the merge sort, and you never gave a thought to, like, is the data here, is the data there, is it this bit, the upper bit, the lower bit? That's the cool stuff to us, is designing these out of transistors and gates. We need to all work together. When you work with the assembly language, you can actually see the bits flowing. That's important to design efficient hardware. So where this comes together is instruction set architecture. Where's that? Processor architecture. What do I mean by that? Every processor has a different ISA. So there's Intel ISA, MIPS ISA, NVIDIA. Instruction set architecture is the set of instructions, registers, memory access, interrupts that processor supports. We call it ISA. Something called ABI, this is on the software side, is everything that's doing the translation. I have a few slides on it in Module 7, and we'll show you, good question, right? How did the variable AVG, average, get to location 600? Who picked that? It was actually the loader, okay? But we'll show you what these middleware tools do and how they make some of those decisions. But that's different. That's just a small part of this class. It's a large part of operating systems class if you take that. This class we're going to design hardware. So one final view is the big picture view. It's good to change level, understanding. We got into the bits and the gates, and now we're going to come back up and we'll go back into the bits. Different view is architectural view. And this is a taxonomy. It's a taxonomy. Who's the SAT person? What does that word mean? See, now when you have your laptop, you can look smart, right? Just Google it. Or you're not. But if you want to Google it, you can. It's department meetings, project meeting, get used to it. What's the word taxonomy mean?
There's a science concerned with classification of species.
Yeah, so that's making it a verb. Taxonomy can be just an org chart, a hierarchy chart. It's a way of making categories. So one way to understand concepts is to put them in groups. There's categories. Okay, taxonomy would be living things. There's plants, there's animals, there's mammals under living, right? And then you got reptiles, and you got, it's taxonomy. So here we have single users. One way to make this a taxonomy of the architectural level, single user systems. These tend to have rich displays like mouse, multi-touch, audio, video, colors. Go up to the next level, servers. We call these multi-user systems. So now even PC is multi-user, but that's okay. Multitasking. So servers, we all know what a server is. Server is mainly interested in throughput, calculating tasks, completing tasks per second. Not so much the user experience, the user interface. Go up one more level, supercomputers, data warehouse. You're going to see what's the difference between a supercomputer, scientific computing, and a data warehouse. This is all about crunching the bits, crunching numbers. This is about storing data and searching and retrieving it. And you probably use some cool data structures from CS1, like binary trees. If you want to find data quickly, organize it in a binary tree, why would you use a binary tree? Someone took CS1.
Because it's a quick decision. It's either a yes or no, and you cut off half the chart each
Yeah,
time.
and you cut it in half every time. It's called bisection method, right? It's actually a log behavior, log-based 2 of n is the number of steps, number of search steps. It's actually a tree, right? So you take the word, I don't even know what's the middle of the alphabet. Root. This is the root node here, but I'm thinking of a word like, starts with M. Monday. Monday's there. And then what's to the left of Monday is something that's less in the alphabet before Monday. I don't know. Letter. Okay. And then underneath there, binary. And so I can look through n things, which have come up a lot when we design circuits because we use Boolean log. Log base 2 is the height of this tree. Is the running time in terms of the number of searches proportional to the number of elements in this tree, the nodes, or the height? The height. Yeah, we just were kids, right? I'm thinking of a number, hot, cold, or whatever, right? It's the same thing as bisection search. Okay. So that's what Google does. That's their only, like YouTube. Profitable business product is they just go and they bring the web in every day. Actually, everything on the internet, they just bring all that data in, then they just chop it up into a binary tree, and then they search it. It's to make it a little bit more efficient than that, but that's basically it. So when you type something, that's why I can find it, because they've taken every page and they look for the punctuation, and they make nodes in the tree, and then they find that page, and they find that data on the different pages. And of course, they look for the trends and try to rank it and see what you click on next. They try to learn over time and they get smarter, but that's the basic idea. So that's data warehouse. And we have one other node in our taxonomy that's commonly used, embedded system. Embedded system has some elements of each one of these. Okay. Embedded system might be a simple processor, more like a single user system, but it might have, some specific numeric processing capability depending on the type of system it is. And that makes it an embedded system. It's something that actually sits inside a device, like a car or a microwave oven, and it's making decisions, controlling a robot. You can't go there and check your bank account or your Facebook, okay, on the embedded processor, because that processor only does certain things. Just takes in data from the sensors. So here's an example of a Internet of Things device. Intel sells this, called it. It's an SD card compatible as far as the pinout and the form factor. It's a Pentium PC with some small amount of memory, okay, not a meg, okay, and some non-volatile memory, some flash, which takes the place of the hard drive, and Wi-Fi, Bluetooth. It's an SD card. So you make these very cheap. And you interface this to devices, and you can then have a computer anywhere you want. So that's the future, and people are going to hire you in the next 5 or 10 years to do these, because there's a lot of money in these things. Where's the money in the quantity? We produce in quantity, this makes them cheap. What's a use case, a business case? You say, you know, why do I care about Internet of Things? I'll use this kind of as a running example because it's very 2015 and I want to add to the slide. But sensor, exactly. So, you know, this is a classic example maybe, but it works for me, is, you know, you don't get flat tires that much anymore, but they run flat or whatever, but every car now, right, has a pressure sensor. It's actually required by federal law, I guess, right? And what's great, right? If you're take 5 tires, you can pop up on your cell phone or your Waze app or your whatever is inside the car, your radio. You know, please click here to schedule an appointment to fix that flat tire, and here's a coupon. They want that. It's very profitable. People want to put these sensors all over the place. People want to put them in your Google wants a Nest, right? They want to put it in your thermostat, and then it's your Wi-Fi for your house. But of course, they find out everything you're doing when you come home from work, and when you do this, and they're gonna. Well, you come home at this time, you know, you want to watch such and such on TV. You come home at this time, you probably want TV dinner. So they're gonna, you know, like there's a big scandal with that. It was spoiling Christmas or birthdays and things. And, you know, spouse goes to the computer, right, on the computer, and all the gifts, right? The guy was just Googling it, or the one was Googling for the guy, and it's like, he knows what he's got for his birthday. And all those search ads, right? AdSense comes up, right? That's going to be AdSense like every day, right? We just walk into a room, right? What was that? Minority Report, right? That's way back. But anyway, right? I think he walks into an airport and it's like, I think he either changed his eye or Mr. Okamoto, welcome to the such and such. It wasn't him, right? But he was using somebody else's retinal scan or something. Yeah. So that's the scary part. But the good part is there's a lot of jobs and they can actually do good things too. Going to save energy and make things better for us and coordination and convenience. And there's security, right? Good. A lot of jobs, right? To make all this stuff work. So here's an example of seeing all these. You're going to say, you know what, this was great, and I sat here and I was entertained or whatever, maybe you weren't. But where do we actually see this in life? These are in your pocket. All 5 food groups working together. Right? We see here processor, CPU speed, so many cores. We'll talk about what these mean. Gigahertz, memory, yeah, gigabytes. We see that. This is actually flash. It's non-volatile. Micro SD. Well, what about links and too many choices, right? It's a funny saying got from IBM is this great thing about standards. There's so many to choose from. You work in Dr. Maloka's lab, they hate it because they have to have, you know, all these different wireless formats, and every phone has to support, you know, a dozen different. You need oscillators, you need the RF tanks. Okay, so sensors. We'll talk about energy and batteries. Okay, so here's our summary. Module 2. Hierarchical levels of abstraction, hardware-software interface. I think the takeaway view is these are some trade-offs between time and space. Hardware and software are actually the same thing, just one is more abstract and another one is more time efficient at a cost of space. Well, what about interaction between processors? Remember we said with address buses, data bus. We'll learn more about that. What is the memory? What's a processor? How do these work together? What's the difference between a compiler and assembler? We need to know that because we want to design hardware. We want to start working with assembly language. It's going to show us the fundamental steps. Good news. We have 2 modules in the rear view mirror. There's only 11 plus or minus 1 in the class. Depends on how fast we go.